The video doesn't seem to be working. It's okay. Good afternoon, everyone. The House of Sultan and Sons Private Limited and Method AI extend a very warm welcome to all the participants of today's Artificial Intelligence webinar. It feels nice to have you all here, and we thank you for that. A bit about the House of Sultan first. Pioneers in the field of book publishing in post-independent India, we cater to students from pre-primary to university level, churning out over 600 regular titles, besides adding new ones to our stable year after year. Known for competently written, elegantly produced, and reasonably priced books, our publications are widely prescribed in reputed schools and colleges across the nation, as well as in some neighboring countries. Our authors are distinguished academicians, professors, and educationists with vast experience and expertise. We are proud to be associated with them. I now introduce you to the host of today's webinar, Dr. Sachin Gupta. Besides authoring into artificial intelligence and data science textbooks for classes 9 and 10, Dr. Gupta is Dean, Research and Innovation, Maharaja Agrasen Institute of Technology, GGSIPU, Delhi. It is a matter of great pride for us that Dr. Gupta's latest book on AI, Decoding Artificial Intelligence, has won the Outstanding Contribution to AI Literature Award recently. We congratulate him for this achievement. Besides, Dr. Gupta has also been HOD, Computer Science Engineering and MCA Department, Dronacharya Group of Institutions, Deputy Director and Head, Computer Science Department, Chandraprabhu Jain College of Higher Studies, affiliated to GGSIPU, Delhi. With a teaching experience of over 22 years, which includes teaching undergraduate and postgraduate students and researchers, Dr. Gupta's academic pursuits have been fairly meritorious, winning him several awards, distinctions, scholarships, including the Certificate of Academic Excellence by GGSIPU. Dr. Gupta has also contributed to various journals, conferences, and books for schools and higher education, both nationally and internationally. His achievements are truly commendable. May I now request the man himself to take you through today's session. Dr. Sachin Gupta, have a great day ahead. Thank you.
Thank you so much, sir. Thanks for the kind introduction. I'll give a very small brief about what we did last time. So any machine learning model requires us to be able to say how good the model is. And there is a reason for it. If you leave machine learning aside, anything which was statistical or mathematical, we were not optimizing by and large. We were trying to find out an accurate result for whatever we were trying to do. Like if we're converting temperature from Fahrenheit to centigrade, you would have an exact result. But with machine learning, they are considered predictive models. They would be taking in some inputs, taking in some outputs, create a model using them, and eventually the model would be used to predict some values which we had not seen prior. That means for some input that we had not seen earlier, we want to predict an output, that what would be the output of this particular scenario. So for these scenarios, wherever we are actually looking forward to predict something on the basis of the model only, where the model itself has been derived, where the model itself has been only based on the type of input that we have and the type of output that we have. If the inputs and outputs are very good, the model would work very fine. If the inputs and outputs are not very good, the model might not work very fine. But how do we test it? So there come something that we know as the metrics for accuracy or the metrics for machine learning models that we work on. During the last session on regression, we discussed a lot of parameters which work in the lines of that how accurate our model is when we are talking about regression, that when we predict a value. Today we are going to discuss classification model. It needed its own complete separate session because uh, it's very confusing to a lot of people that we see what is precision, what is recall. There is a lot of confusion that which has to be used when, what is the confusion metric, and it's considered very confusing for several. So for today's session, we are just simply trying to keep it as simple a discussion as possible for making the classification models understandable. What are their metrics? And we have some sample case studies at the end of the session so that you'd be able to understand from the perspective of CBSE questions, that the kind of question that have previously come in the paper, that what to apply when. So let me share my screen quickly and then we can take it forward. I hope my screen is visible to everyone. If you have
Yes,
any
it is.
queries, please post them in the chat box so that I'll be able to see them and we'll answer all of them. So first thing first, what is the classification model? Whenever we are trying to make a prediction, which is a class, that means whenever we are trying to actually isolate or separate two different or three different or multiple different components into each of their own classes. So model which predicts a class is a classification model. Like you can say a model that predicts an input sentence language, whether it is French or Spanish or English or Italian, that is classification. Or a model that predicts tree species based on the leaves or some other feature. Or a model that can predict a positive or negative class for a particular medical condition, like somebody has COVID or somebody may not have COVID. So that may be a positive, yes, he has COVID, negative that he has not. And in contrast, the regression models predict the numbers rather than classes. They are like, I know that this is the location in which I have a house. These are the number of bedrooms. This is the total area of the house. This is the garage or the parking available, proximity to schools. And I want to predict the price of the house based on other houses in that vicinity. That is a regression problem. So our classification can be either binary, where we are like separating only two classes, like cats and dogs, or apples and balls, or any two kind of uh, instances. And there can be multi-class classification like tree species, where we said that the apple varieties, Fuji or golden apple or Kashmir apple, that we want to predict between multiple classes, or we want to classify a particular image as a different. So dog breeds can be one example, or cat breeds can be another example, where there can be multiple possible outputs of the same. For each classification, there is some concept that we call as thresholding. This is usually missing in most of the uh, tutorials or most of the video that you would watch. That what is thresholding? So thresholding is, first understand that when I classify something, when I classify a dog versus a cat, I would be able to say with certain probability that I'm 90% sure that this image is a cat. I would never say that I'm 100% sure. By and large, some models may do that, but in reality, in real life, we would always say with some possibility that, let us say this image 90% sure this is a cat, 10% I'm not sure. So the basic model for classification that we know as logistic regression, it returns a probability. You can use the return probability as it is, that say the user will click on this ad, the probability is 0.00023. Okay. Or we can convert the return probability to a binary value, like this email is spam or this email is not spam. That binary value would be yes or no, spam or not spam, dog or cat, like that. So whenever we want to map a logistic regression value, like the probability that we have seen up here, into a binary category, we must define a classification threshold. It's also called a decision threshold, that on what basis would we, or on what probability value would we classify something as a cat, and on what value of the probability we are going to classify it as a dog, or on what value of, let us say, I look at some email and my logistic regression says that it has a probability value of 0.38 to be spam. Then whether I want to classify it as spam or not, that depends on that what is my threshold value. If my threshold is less than 0.3, it would classify as spam. My threshold is more than 0.3, it would classify probably as non-spam. That is the kind of example. So it is very tempting to assume that the classification threshold should always be 0.5. That 50% of the images that a model has seen would be cat, 50% would be dog. So there can be a classifying threshold value of 50% or 0.5, but that is not usually true in most of the models. So we have to tune the threshold value every time that we are trying to classify. Please feel free to question anything wherever we have a issue, because the topic itself is a bit typical. So let us understand thresholding further. In binary classification, thresholding is a number between 0 and 1. That is the outcome of your machine learning model, which converts the raw output of logistic regression into a class that would be predicted as a positive or negative class. Now, classification is something that we choose. The threshold value is it's a hyperparameter. It's something that right. I heard somebody. Please switch your mics off. Thank you. So a logistic regression model predicts a raw value between 0 and 1. If the raw value is greater than the classification threshold, we say a positive class. If the raw value is less than the classification threshold, we say a negative class is predicted. Like for COVID, again, we would be saying that the person is positive or not positive would be based on the classification threshold. So assuming if we set up the classification threshold as 0.8. So if the output of my logistic regression comes to be 0.9, then the model is going to predict a positive class. If the raw value that the model predicts is 0.7, then the model predicts a negative class. So it is not necessary that the threshold would always be 0.5. This would be very essential to understand. Thresholding, second point is that we decide that what thresholding value we want to have, because that would be basis on our domain knowledge, one. That may be possibly that we are actually calculating a lot of parameters on the basis of which we decide that the threshold value should be this. Or we may keep on varying the threshold value to see how well our model performs with different threshold values. That is the basis of this tutorial. So let us understand confusion matrix, what is true positive, true negative by the Aesop's fable. That all of us have heard the story of the boy who cried wolf. A shepherd boy gets bored tending to the town's flock. To have some fun, he cries out wolf, even though there is no wolf in the sight. The villagers run to protect the flock, but then they get really mad when they realize the boy was playing a joke on them. And this happens a lot of time, not just once. It happens a lot of time that whenever he gets bored, he cries wolf. So one night, the shepherd boy sees a real wolf approaching the flock and calls out wolf. The villagers refuse to be fooled again and stay in their houses. The hungry wolf turns the flock into lamb chop. The town goes hungry. So that is the kind of story that we have already heard since our childhood. Let us now convert it to a class confusion matrix for us. So wolf is a positive class. That means we say the presence of wolf, the wolf coming is a positive class. No wolf is a negative class. Let us summarize the wolf prediction into a 2x2 confusion matrix that has all 4 possible outcomes. So confusion matrix is an n cross n table that summarizes the correct and incorrect predictions that a model made. For example, if I have the ground truth as that I am predicting tumor and there is tumor, it's a true positive. The ground truth is that there is actually tumor and I am predicting it to be a non-tumor. This is a false negative. If the ground truth is non-tumor, that the person does not have tumor, and I predict it to be tumor, then that's a false positive. That is something that the actual ground truth is false, but we are predicting that true. And there is something like the tumor is not there and we are predicting it also as non-tumor. That is would be a predicted value. That is a true negative. So true positives and true negatives are both close to ground truth, and false positive and false negatives are both away from the ground truth. So this is one of the way that we are going to look at a classification confusion matrix that we have to define. Then let us look at the Aesop's fable again. So you were talking about a true positive, which is an outcome where the model correctly predicts the positive class that we see from the confusion matrix definition. A true negative is when the model correctly predicts the negative class. So whenever there is a term true, that means you are close to the ground truth. Whenever you see the term false, that means you are away from the ground truth. So ground truth is that the person does not have a tumor, right? And if we are saying predicting it as tumor, that means we are away from the ground truth. Similarly, when the person has tumor and we are predicting it to be non-tumor, we are away from the ground truth. So close to the ground truth, you are having true positive or true negative. Away from the ground truth, you are having false positive and false negative. This is a very simple way to understand this. So going back to the boy who cried wolf, our matrix would look something like this. All true positive is the reality or the ground truth is the wolf has threatened the flock. The shepherd said wolf. That means he predicted. So outcome is shepherd is a hero. This is a true positive. That ground truth was there was a wolf. Shepherd predicted wolf. So both of them match. It's a true positive. True negative would be no wolf threatened. Shepherd said no wolf. And outcome is everything is fine. That means both of them are close to the ground truth. But on the other hand, in reality, if a wolf threatened and the shepherd said no wolf, that is a false negative. And in reality, no wolf threatened and the shepherd said wolf, that is a false positive. Go back to what is positive in our case. We say wolf is a positive class. So when shepherd says wolf, the class is based on prediction. That means this says what is the prediction. So if my prediction is positive class and it is not happening in reality, then I say this is a false positive. I hope so far, so everything is clear. In case not, please post your queries. I have access to the chat window. Okay. No queries yet. Let us go ahead. So there are some metrics that we can define here. Accuracy for one. Accuracy is one metric for evaluating the classification model. Informally, accuracy says what is the fraction of predictions our model got right. That means what predictions are correct. In this is always correct. True positive is always correct. That means the prediction and the ground truth match. True negative is also correct. The prediction and the ground truth match. In these cases, the prediction and the outcome do not match. So look back at it again. Accuracy says the number of correct predictions. So obviously the correct predictions are true positives are correct predictions. True negatives are also correct predictions. But the total number of predictions is all four. The true positive, true negative, false positive and false negative. So whatever prediction that we are making, they are contributing to the total number of predictions, out of which some are true positive and some are true negative, which are correct. And if there is a false positive and false negative, they are incorrect. We are not considering them in the calculation of accuracy. So let us try calculating the accuracy of a following model that says 100 tumors as malignant or benign. And we have if the true positives were 1 and the true negatives were 90, and the total prediction that we made was 1 true positive, 90 true negative, 1 false positive, and 8 false negative, then the accuracy of the model is 0.91. Okay. Let's say reality, ground truth is malignant, that's the cancer, ML predicted that yes, it is malignant. That's a true positive. The number is 1. We are taking the value 1 here. A false positive here, reality that the tumor is not cancer, but our prediction is that it is cancer. Then that is a false positive. In that case, the false positive result, the total count is 1 that we are substituting here. A false negative where the reality is actually cancer and the ML model predicted that it is not cancer. There are 8 such cases which we take as false negative. And for the true negative, the reality is that it's not cancer. And ML also predicts that it's not cancer. Total 90 results are there that we add in. And the accuracy is 0.91. So I'll hold up here and ask you that how good the model is. How good do you feel the model is with a 91% accuracy? The model should be good? By and large, most of us will say, yes, the model is possibly good. Let us analyze it. So accuracy is 0.91. It comes out to be 91% or 91 correct predictions out of 100 total examples. That means our tumor classifier is doing a great job. But let us do a closer analysis. Out of 100 tumor examples, 91 are benign. That is 92 negatives and 1 false positive. So false positive is also benign, where I said that the model predicted malignant, but it was not malignancy. It was reality. In reality, it was benign. So there are total 91 cases which are actually benign. All right. So 91 are benign, and similarly 9 are malignant. Out of 91 benign, the model correctly identifies 90. That is good. But out of the 9 malignant tumors, the model only correctly identifies 1 as malignant. So it's a terrible outcome because now 8 patients out of the 9 who had cancer, my model is not checking that. My model is simply saying they do not have cancer. So this false negative is a very big problem in this scenario because this value of 8 is a problematic scenario. So 91% accuracy seems good, but another tumor classifier model that always predicts benign would actually get the same accuracy in our example. Right? So the problem is the false negative is a big problem in this scenario. We are not actually having a model which is good because it is letting even people who have cancer being detected as having no cancer. So that is a problem with accuracy. So accuracy does not always work. It just gives you a base value of how good your classification model is working, but only in conjunction with several other parameters that we are going to later go on. So accuracy does not tell the full story when you are working with a class imbalance data set. Why did this happen in this case? So when we train a machine learning model, we give it a lot of examples. Like majority of the people in the world would be having non-malignant tumors, if there are tumors. Only a few would have a malignant tumor. So my classes are imbalanced, that the machine which is learning, the training data has a lot of examples of those which are non-malignant and only a very few examples of those which are malignant. So the training data itself is skewed. This skewness actually causes this problem that there is a class imbalance data set where positive class may have a lot of examples, negative class may have a very limited number of examples. Take another example, for instance, that credit card fraud or UPI fraud, with UPI going into 6 million transactions like per day, there would be barely a few out of them which are going to be fraudulent. Now, how do we train a machine learning on a class imbalance data set where majority of the examples are true positive or true class, but only a very limited examples are on the negative side? Then that class imbalance actually causes a lot of problems when we are working with classification, because there is no true representation and both of the parties are not equally represented when it comes to the training. So obviously the outcome comes into the testing also. So there come precision. I'll define precision as what proportion of positive identifications were actually correct. My model identified some numbers as positive, how many of them were actually correct? So true positives versus divided by true positives plus false positive, that whenever the model said it was positive, how many of them were true? That is the definition of precision. Okay. So if a model that is producing no false positive, the precision would be 1 to that extent. So if there is 0 false positive, it would be 1 by 1, whatever number it is, that number divided by itself, it comes out to be 1. It does not happen in real life per se. Most of the time, the precision would not be 1. Most of the time, precision would be something less than 1. So for the analysis of tumors, the same example that we were having, true positives were 1, false positives were 1, false negatives 8 and true negative 90. If we have to calculate precision here, then using the formula, we have the true positives as 1, false positive is 1. So there is a 50% precision. Our model has a precision of 50%, that whenever there is the model predicts if the tumor is malignant, it is correct 50% of the time. Not a very good scenario again, because if a model is predicting that somebody has cancer and it is saying only half of the time it is correct, then that means there is some very big problem with the model that we are using. All right. So whenever there is a high precision, it indicates that the model produces fewer false positives. Right? So high precision means that this value should be as less as possible. By simple mathematics, the less the value of false positive, the higher the value of precision would be, because this is a term in the denominator. So model produces fewer false positives, the precision would be always high. All right. So here the model is producing fewer false positives, but it is also producing fewer true positives also. So that is why the precision is low. Right. Then recall says that what proportion of actual positives were identified correctly. So actual positives were that in this case, the actual positive is that you have the true positive and you have the true negative. Wherever there is no false negative, the model would have a recall of 1. Right? The ratio of true positive divided by true positive plus false negative, that is called a recall. So whenever there is a high recall, we may implicate that the model identifies most of the relevant cases. That means it's identifying most of the relevant or most of the cancer cases, but it could produce more false positive also. That means in addition to correctly identifying the true cases, it is also identifying some of the false cases as true. So that is something that happens in the recall scenario. So for calculating the recall, again going by the formula, we would be able to say that the true positive was 1. The false negative here was 8. So if we reduce the value of false negatives, we would be able to have a high recall. But if the false negatives are higher, then the recall value would be very less. So model has a recall value of 0.11. That means it correctly identifies only 11% of the malignant tumors. This you can also see with the help of the analysis that we had prior, that out of 9 malignant tumors, the model only correctly identified 1 as malignant. This is 11% recall value, that the model correctly identified only 11% of the malignant tumors, that there were total 9 malignant tumors, out of which it predicted only 1 correctly. So that is a problem with the recall. Which one to use? Well, I mean, whether accuracy is good, whether recall is good, whether precision is good, that belongs to a specific case that wherever we are going to discuss it. So go back to our classification threshold. Let us check how do precision and recall change when we change the threshold. So precision and recall are often counter to each other. So when we are trying to improve precision, we might have to typically reduce recall and vice versa, but it's not necessary. Sometimes we may have high precision and high recall both. So it's not a rule, but majority of the cases it happens that when we are trying to improve the precision, the recall would be a bit reduced. And look at this example. where you may have to count that there are certain number of true negative, there are certain number of true positives and false positive. So this category is before the classification threshold, anything would be categorized as negative. After the classification threshold, anything would be categorized as positive. So these were some negative, these were some false negative. That means the value actually was positive, but it was classified as negative. And here there was some value which was actually not spam, but it was classified as a spam. So this is a classification threshold which is going to identify. Now how to count? You just have to count the red and the green values. So anything above the classification threshold is considered negative, and anything below, sorry, and anything above the classification threshold is considered positive. So based on the counting, there are 8 true positives. True positive means this is 1, 2, 3, 4, 5, 6, 7, and 8. So there are total 8 true positives. There are 2 false positives that you can see from here. And similarly, if you count the false negatives and true negatives, you'll be able to count that there are 17 true negatives and 3 false negatives in this scenario. So our classification matrix is on the basis of the threshold value that we have just decided. So here, precision says that which emails were flagged as spam and they were correctly classified. That means that how many true positives were there divided by how many false positives in addition to that were there. So total number of predictions made were on the true positives, false positives were 10, and we had 8 out of 10 correctly identified as spam. So that we say precision is 80% or 0.8, or 8 mails out of 10 would be classified spam when they were spam. Recall by the formula, it would be 0.73, that we have 8 true positives and 3 false negatives. So there is a 73% or 0.73 as a value of recall. Both are fairly good. I wouldn't say this is bad. I wouldn't say this is bad. Both are fairly good. The recall is also good. The precision is also good. The model is working good. Now, keep this in mind that the threshold was there. Let us try to move the threshold a little towards the positive side. And we have moved the threshold a bit. So you see the true positives are 1, 2, 3, 4, 5, 6, and 7. So there are 7 true positives, only 1 false positive, but the other count is changed. So we shifted the classification threshold a bit. Now that is what? That false positive decreases when we have shifted the threshold. But at the same time, are the other values changing? So see, precision now becomes 88%, that the precision of the model is now doing better, while recall goes for a toss. The recall is not so good anymore because the false negatives increase somehow. So false negatives, which were only 3 previously, now we have got 4 false negatives, which is causing the trouble of decreasing the recall. So whenever false negatives increase, the recall decreases. And whenever true positives increase, whenever the false positives decrease, the precision increases. By the same formula that you can see, whenever false positive decrease, the precision increases, but whenever the false negatives decrease, the recall increases. Correct? So we saw 2 examples of shifting the classification threshold from a value to more on the positive side. Let us see an example. We are shifting the classification threshold more to the negative side. So here we have 2 positives as 1, 2, 3, 4, 5, 6, 7, 8, and 9. There are 9 true positives, but the number of false positives also increased. Similarly, on this side, true negatives possibly remain the same, but the false negatives decrease. So by my definition, when the false negatives are decreasing, the recall should increase. When the false positives are increasing, the precision should decrease. I repeat, so false negatives are decreasing, the recall should increase. And if the false positives are increasing, the precision should decrease. And let us look at the results now. So look at it, that false negative decreasing made a recall went up, to 0.82. From initial 0.73, then went to 66%. Now it is 82%. But the precision has gone down. From the previous example, it was 88%. From the original, it was 80%. And now it is only 75%. So this makes you understand that the classification threshold which we choose would have a very huge impact on the precision and the recall value that we are working with. I hope there are no queries so far. Nothing. Thank you. So let us do some examples on accuracy from the people who are here. Which of the following scenarios would high accuracy suggest a model that is doing a good job? So the first is, let us start from the bottom. There is a deadly but curable medical condition. It afflicts only 0.01% of the population. Now my machine learning model uses the symptoms as features and predicts that accuracy is 99.99%. That means 99.99% it is predicting. The accuracy is 99.9%. Then an expensive robotic chicken crosses a very busy road. The machine learning model evaluates traffic pattern and predicts when the chicken can safely cross the road. Now this is very expensive robotic chicken, and it can safely cross the street with 99.99% of the times out of 1,000 times per day. Take them to the actual values. Check out this 99.99% accuracy, that the model is much better than chance. Chance is that the probability, if there were no machine learning model, the chicken would still cross the road. It would be hit by a car. But with the help of machine learning model, we are saying that 99.99% times it would be, the machine learning model would be correct, that it can cross. If the chicken is expensive, then on the average, because 1,000 times a day it has to cross, in 10 days it would be crossing 10,000 times. 99.99% means that 9,999 times out of 10,000 it would be not crashing, but one time in the 10,000 times it would crash. That one time is causing a very expensive damage to the chicken, and that is something that we can't do. So even with the accuracy of 99.99%, this is not good. Similarly, with the deadly curable disease, that the disease strikes only 0.1% of the population. My ML model predicts an accuracy of 99.99% with this. Now, there 99.99% it would predict that it is not sick. Mistakenly, if you are predicting not sick for a person who is actually sick, even for a 0.01% of the population, then this could be deadly for the person. So accuracy is again not a very good model here. The third example said that I'm dropping a ball on a spinning wheel and it eventually lands in one of the 38 slots. Now, our model can predict that the slot in which the ball will land with the accuracy of 4%. That the model says it would land in 2, it lands in 2, but the accuracy is only 4%. Now check how accuracy can be good here. That if I were making a random guess, it would be 1 per 38 of the times. Right? 1 by 38 of the time means the accuracy is 2.6% if it was random. If it was just prediction, possibility of that which one would it land in, it would be 1 out of 38, anyone. But if our model accuracy is only 4%, it is still a much better improvement over 2.6%, and this is going to give you better chances of success at the game of roulette. So that is again an example where even a small accuracy of 4% is better than not using the machine learning model in this case. Now let's check for precision and recall again. There is a classification model that separates email into two categories, either spam or not spam. If we raise the classification threshold, if we increase the classification threshold, what happens to the precision? The question is that the precision would increase, it would definitely decrease. probably decrease or probably increase? I want people to be able to answer in the chat box. The question is there. I'll look at your answer. I'm saying that I'm increasing the classification threshold. What happens to precision? Would it definitely increase or decrease, or would it probably decrease or increase? A, B, C, or D? If anybody would like to answer. Anyone? Probably increase, Ashish sir says. Okay, what I just did, I'm going back to the previous slides and let us check the answer to this question. So we had a classification threshold earlier. We are now saying we are increasing the classification threshold a bit. When we increase the classification threshold, the precision of the model probably increases. It's not necessary that it would always increase. This would depend on that what are the red dots, where are the red dots placed. So there is a possible increase in the precision whenever I am actually going to increase the classification threshold. So in general, raising the classification threshold reduces false positive. So precision raises usually. Similarly, if we are going to raise the classification threshold, what happens to the recall? Should the recall increase, decrease, always stay constant? So there is issue with the recall again, that if we are increasing the classification threshold, the false negatives are going to reduce. So recall would always decrease or stay the same. So raising the threshold would increase the number of true positives to decrease. We'll call the number of true positives decrease, and thus the number of false negatives to increase or stay the same. So recall would always stay constant or decrease whenever we are raising the classification threshold. All right. Going ahead. This is one going to be very confusing thing, that if we have both precision and recall, why these are used as metrics? I wouldn't actually compare a model to itself. But if, let us say, I created one model and my friend also created another model. For my model, which is A, if my model has better precision than B, then is my model better? Would I be able to say so, that my model is more precise? Or if my model has better recall than model B, then model A is better? Or if model A has better precision, better recall, both as compared to model B, then the model A is probably better. By intuition, you understand, by whatever we have learned so far, that if a model has more precision, it's not necessarily better. If a model has better recall, the model is not necessarily better. But if I've got better precision and better recall both, so if a model has both high precision and high recall, it is probably better than both of them. Okay, there was another option that says second option. Fine, same. All right. So in this case, my choice is, if a model has better recall, model A is better. It's not necessarily true. Because if the recall is good, precision might not be so good. So we have to see both precision and recall. If the model has better precision, that might be a large reduction in recall. So we have to see both. But if I see that the model has both better precision and recall, the model A is probably better. So this is the most plausible, correct answer for this scenario. So to summarize, precision focuses on reducing false positives. That precision has the false positive in the terms of a denominator. Recall concentrates on identifying as many positive cases as possible. So it tries to increase the number of true positives in this case. So false negatives may or may not increase in that scenario, but we were trying to create as many true positives as possible in recall. Consider another case. let us say we are trying to design a classifier which detects fraud transactions in a financial system. So fraud transactions have what? They prioritize catching genuine fraud activities. We want to catch all the genuine fraud activities. But if we are going to flag too many innocent transactions as fraud, the customer would be inconvenienced. Like I make a transaction, I want to purchase some product, I make a transaction and suddenly they say, no, this transaction is not valid. That is a false positive. We do not want to do that. They want to only catch the transactions which are fraudulent. So in this case, recall takes precedence. Recall means we want to catch all the fraudulent cases. So we would make a fraud case as true positive. We want to increase the number of true positives as much as possible. तो यहाँ पे हम लोग false positive avoid करने को इतना precedence नहीं है. We can, अगर if there is a person जिसका transaction flag हो भी जाता है by mistake that this was a genuine transaction but was flagged as a fraudulent, in that case that inconvenience is okay, but we want to have as much recall that we want to catch as many fraudulent cases as possible, even at the cost of precision, that even if we have some false positive, we would be able to take that. Okay, let there be some false positive, but we don't want to miss out any of the fraud cases. That is the case one. So this is some kind of example that CBSE usually asks in their question paper, that if given this scenario, what takes precedence? So another case is a medical diagnosis, where if I have to identify all the ill patients accurately, high recall is crucial. We can have some non-ill patients also identified as ill. That would work, because in that case, worst case is we are just simply going to start their treatment where they were not ill. But if we are going to let out a person who was ill, and if we did not catch that, in that case, that person is going to possibly get very ill or may even die. So high recall is absolutely essential here. Now, email filtering, whenever we are classifying the email correctly, we want to prevent all the unnecessary distractions. That means if an email was spam and it lands in your inbox, it is very inconvenient. So you do not want any of these spam emails to come into your inbox. At the cost of, if there was a genuine email which would actually go into spam, that might still be tolerable. But otherwise, we want all the spam to be at least filtered. So here, high precision is necessary. Right? The false negatives are actually false positive or false negative. Check out. So sometimes neither precision nor recall is alone to sufficient. We have to actually take a balance of both. There, F1 score comes into picture. So F1 score is the harmonic mean of the precision and recall value that we do. Take another case, for instance, before we start taking questions. So this is again from a CBSE case study. A bank wants to develop a credit default prediction algorithm, that I go to them for a loan and they want to identify whether to give me a loan or whether to not. So they want to predict that whether I would default or whether I would not. Check out what the answer is. So here precision would be, what is the fraction of truly risky loan applicants among those which are identified as high risk? So algorithm says this person is high risk, and out of that we want to say who are truly risky. So recall is the percentage of genuinely risky relative to all high risk applicants. And here precision and recall both are essential, because high precision rate keeps down the expense of investigating false positive. So my system flagged that this person may be high risk. I would have to go investigate them. We do not want to do that. A strong recall allows to safeguard bank against the defaulters. So to avoid financial losses, a strong recall is also necessary. So in this case, we can't say high precision is good or high recall is good. We have to have both of them. We want to have both of these to be there. Take another example, which I leave to you, for instance. We say there is a large e-commerce website which seeks to enhance its email marketing campaign by implementing automated spam detection software. how precision and recall impact. Why recall may be more critical than precision in this situation? Can somebody think about why recall may be more critical? Let us take the answer. Precision says how many of the promotional email they reach the recipient interested in purchasing from the site. Recall says that is my algorithm able to isolate the spam messages targeting the active buyer? So recall has a major role that all the users who have actually enrolled for this and getting a targeted advertisement, good. But if there is a malicious promotion, if there is some mail coming which actually leads them to a wrong site where the customer may feel that he has been cheated, in that case, that actually causes trouble. So recall plays a very significant role in this case. Right. So far, for whatever we had to discuss, I hope precision and recall are clear so far with what case we want to apply which one. And I am going to now open the stage for any question that you may have related to precision, recall, classification, confusion matrix, anything for that matter. I think the session went on a bit longer than expected, but required. I take it that there are, Ashish sir, are there any queries on
No questions
YouTube?
yet. No questions.
All right. Okay. I think we can close the sessions and we can throw open the queries to any people who are watching the video later. You can reach us out on sachin.gupta@methodai.com, or you can text us on WhatsApp if you are in one of our teacher group. Thank you so much for having us on this session. We can close the session now.
A very informative and interesting session. Thank you, Dr. Gupta, for that. This was the last of our class 10 sessions for now. We'll soon be back with a series of sessions for class 9, about which the participants will be duly notified well in advance. Thank you, everyone. Stay safe.